Okay, so last time we talked about the duality of Platonic solids, and we learned how to take a Platonic solid P and geometrically construct the dual Platonic solid P star. And so far we've mainly been talking about geometry, but now I need to talk a little bit about group theory. And our main goal is to understand the groups of orientation preserving symmetries of the Platonic solids. Now when I say orientation preserving, I mean that no reflections are allowed, only things like rotations. So if I were to reflect the vertices of a cube in some axis, then that doesn't preserve the orientation. The order in which the vertices appear gets switched around, and I don't want that to happen. So I'm only going to allow rotations. So that's going to be the symmetry group of a Platonic solid. So what I eventually want to talk about is the famous orbit-stabiliser theorem, and that's going to help us classify the symmetry groups of the Platonic solids. But in order to do that, we'll need to introduce something called a group action. So let's talk about group actions. Group actions. So let's define what I mean by a group action. So here's a definition. Okay, so a group G, so G is a group, acts on some set X, so acts on a set X. If there is a map, so if there is a map from G cross X to X, so this takes an element in G and an element in X and gives me back an element in X, so G is acting on the set X, and I'm going to write this map as G, X goes to Gx. And so if E in G is the identity element, so that if E in G is the identity, then the following two things hold. And what are these two things? Well, the first thing says that if I take my identity element and multiply it by X, then I just get my original element X back. So that's true for all X in X. So no surprises here. That's typically what the identity element does. So what's our second condition? Well, our second condition says that if I've got G and Hx, then that's the same thing as doing GH of X. And when I write GH next to each other, that means I do H first and then G. And that's true for all GH in G and X in X. So this definition might look a little bit abstract at this point, so it's best to illustrate this with an example. So let's have an example. Let's use Sn. So let's say Sn, that's the group of permutations on n elements. So let's investigate how this affects this set n. We want to see how what this group action does. Okay, so what's in this Sn group? Well, we've got a permutation, so we've got something like 1, 2. That's an element in the group of permutations. And what does this group of permutations, what does this element do? Well, it takes the element 1 and swaps places with 2, so it's a transposition. And this element lies in Sn. So this is in G. So in this case, G is Sn. And how does this act on, say, the element 2? And this element 2 also acts in, lies in this set. So what does this do? Well, what happens is it takes 2 and sends it to 1, right? Because 1 and 2 swap places. So this becomes 1. So notice what's happened here. Well, this group has acted on this set in the following way. Well, I've got an element in G and an element in X, and it's given me back an element in X. So that's what the group action has done. In this case, the group action was this permutation, and what it's done is it's taken an element in the set X and it's given me another element in the set X. That's what I mean by a group action. And more generally, when we look at group actions in the context of Platonic solids, so if I've got a cube like this, and let's say I label some of the vertices as follows. So if this is the first vertex, this is number 2, number 3, and number 4, and let's say I rotate this 90 degrees about this axis. So this is an axis going through the top face and the bottom face, going right through the midpoints of the faces. So what's the end result? Well, let me just draw another cube and let's see what the end result is. Well, what happens is that the vertices get permuted, so they move around. So the first vertex ends up going over here where the 2 is, so 1 ends up moving places from here to here, and likewise 2 ends up moving here, 3 here, and 4 here. So that's what I meant by orientation preserving. The order in which the vertices appear doesn't actually change. My picture changes though. Okay, so this is an example of a permutation on the vertices, and this is a group action of the symmetry group G, and we will explore this further in the next video.